Welcome to the Knowledge Graphs seminar. Today, we are in the week 10 of the course and in the final session, where our focus is going to be on what are some of the research issues on knowledge graphs. We are fortunate to have with us two extraordinary individuals who are one of the most dynamic and visionary speakers of our field. Professor Jim Handler, he gave us the slogan, "A little semantics goes a long ways." It has inspired so many people that communities have formed around it to realize this vision. Professor Lennart is the creator of the richest and most detailed computational model of human common sense that exists today. We are hoping to hear from them their commentary on the current state of knowledge graphs and get their guidance on where the field should go next. We are going to begin with Professor Handler. Jim, over to you.
Thanks. Should I share my screen?
Yes, please.
Okay. So it's really a pleasure to be here, see people, and particularly to, okay, why isn't it sharing? There you go. I have 200 open windows at the moment. I'm trying to find my PowerPoint, which was at the top of the stack when I tried it before.
Well, if things go badly, you can always pretend that your Zoom connection is freezing up or something.
You know, all right, I can't hear you. Doug, I can't hear you.
I have your slide, Jim, if you need me to project.
I'll have them in a second. Just
they have an application that actually produces that effect for people who want to get out of Zoom phone calls. You know what they call that application?
What is it?
Zoom.
Yeah, I always joke that the best thing about Zoom is you have an excuse for being late. The bad thing is it's usually true.
Michael, if you didn't want meta level jokes, you shouldn't have invited me.
Yeah, either of us. That's right. You know, so one of the first talks I ever saw in AI was Doug Lennett's Computers and Thought Talk. So yes, a brilliant talk, and I still remember many of the jokes he told that day.
1977, and I've changed at least half of those jokes by now.
That's right. Okay, so in theory, I'm sharing, except I'm just
saying it's working. It's working. Go ahead.
You can see it.
There we are. Okay, who can see your message? Okay. All right, so it. So I'm calling the talk Knowledge Graph Semantics, but what I really should call it, if it'll let me advance my slides, there we go, is Knowledge Graph Interoperability. So, I'm all about the web, and everything I've done has sort of focused on really how the web changes how we do things, how we use the web. Nowadays, that's pretty simple, pretty obvious, like the fact that we can hold a class like this. But, when I started doing the web stuff, it was a couple years old and took a while. But to me, what the web has always been about is sharing and linking. And so as we brought AI to the web, a lot of it's been about sharing and linking AI. And so I'm going to sort of do a quick wander through. For some reason, I can't see the top of my slides, which doesn't help. Give me 1 second. Okay, but anyway, going back a couple decades, so around 2000, the web was growing. We had all these siloed search engines.
Jim, if the top of your slide says ancient history, we can see the top of your slide.
Yeah, no, I know you can see it. I can't. Okay. It's not closing the little window that for sharing for some reason. I don't care. I'm just going to ignore it. So we were looking at the fact that, the social web was just taking off. Everyone thought that the application that was going to be the killer app of the web was this thing called Flickr, which didn't actually end up being the killer app, but it led to more social things, stuff like that. But the real problem was everything was still done on basic hyperlinks, and we were trying to come up with a different approach. So in those dinosaur days, the idea was, if you want to do AI, discover stuff on the web, process it, do things with it, we needed a model. So 2001, we wrote, I was lucky enough to co-author an article with Tim Berners-Lee and Aura Lasala, where we provided a vision of a web where what we would now call knowledge graphs ruled. And, we can get into quibbling over, were we talking about the same thing or different things? And I have a whole different talk on some of that history. But the key idea was this was all about interoperability. But what we were thinking was that the interoperability would primarily be done by reasoning over how things were related. And that was not totally wrong, but sort of the use case was that the web would be at a size where if we pulled stuff together and reasoned over it, we could do cool things. But even though we were in the exponential growth, I don't think any of us really realized just how exponential that growth was, except maybe Tim and even Tim, I think, was thinking in a different direction than where the web ended up going. So sort of as we moved from the 2000 years and started really getting into the growth of data on the web, one of the things we were really, so a lot of the early semantic web vision quickly morphed by about 2002, 2003 into what was being referred to as the web of data. Tim and I have another article that's not as well known that came out in about 2004 in the web of data. Maybe the fact that we published it in Japanese is why it's not as well known. There is an English version somewhere around. But again, what we talked about was how database access from the web was growing. And sort of over the next few years, you had these powerful knowledge development tools starting to grow. And then, of course, deep learning came along by 13, 14, and suddenly really powerful tools can be done. But all of these tools need a lot of data. And so the things that are producing the knowledge graphs want data. They're very data intensive programs. But the other thing that was going on was the open data movement. So lots and lots of free your data on the web. Put your data on the web in a machine readable form. And so the notion of semantic web was kind of morphing into this notion of linked data, evolving the web into a global data space, right? And a lot of that view was based on this notion that what we wanted was the ability to take these data sets, describe them in some kind of machine readable way, and link them together. And this started growing. We created something called the Linked Open Data Cloud, which is what this is about. Probably the best known thing in it is the very center, which I realize is too small to read in this version, but that's Wikidata. I'm sorry, that's DBpedia, which then eventually became Wikidata. So if we did this today, it would be different. The other thing is that circle in the middle is as big as any other circle, but in fact, some of these other circles, the people who defined it were the people who created Wikipedia, and they said no circle can be bigger than this one. So some of these other circles really dwarf this, the ones in bio and government and things like that. But Wikidata turned out to be the really useful thing, DBpedia into Wikidata, because it was able to consume a lot of what people were doing and put it in machine readable form. But it wasn't so much that you were using Wikidata to answer questions. It was you were using Wikidata to put things together, to get interoperability. So the original semantic web version was kind of interoperability between applications. If you go back and read the original article, we talked about, people trying to schedule, and two people trying to schedule their parents' medical appointments. And even today, 20 years later, all of those things can be done on the web with different apps and different websites, and you still can't put it all together easily. So the whole idea was interoperability. And so by 2010, we had moved to this notion of data interoperability. And so that started growing. And then we got to where we were looking at the increase in unstructured data. So, nowadays, what we're really looking at a lot is unstructured data use. So powerful knowledge graph tools are evolving, especially as we have now the graph neural networks and things like that. These tools can consume larger knowledge. Well, can create. That really should say could create large knowledge graphs, not consume large knowledge graphs. And these knowledge graphs are growing within, but not between silos. Right. So pretty much where we start to see any kind of interoperability between knowledge graphs, mostly it's being powered by something like Wikidata or some other single system. So to put it in the old terms, may remember the ontology term. We're looking at a common ontology in some ways, and there's still a lot of interest in creating ontologies, discussing ontologies. Ontologies power some of by a different kind of view, are crucial to some of the deep learning stuff, knowing which things go into what categories to look for when you're training the thing. But you're still primarily looking at these things in silos. And I haven't had a chance to review everything you've seen in this class, but I've looked at some of them. And you have a lot of different things that are looking at we have the Amazon knowledge graph, the Google knowledge graph, the this knowledge graph, the that knowledge graph. So it just feels to me very much like first the documents on the web circa 2000, then the data on the web circa 2010. So now it's the knowledge graphs on the web circa 2020. So this has all been a way of sort of introducing the main thing I want to get to, which is how do we get these knowledge graphs to work together? So how can we create open or interoperable knowledge graphs that could power these new and innovative applications? A couple of the ones we've been looking for in my laboratory include sort of general knowledge graphs that could be interoperable with specialized knowledge graphs. So for example, health knowledge graphs. And even more fun comes when you start looking at this with some kind of personalization. So the term personal health knowledge graphs is something we're using in a big project I'm involved in. This is sort of a conceptual view of what we're talking about, but being able to pull together both this kind of general large-scale information based on, clinical record mining, image mining, genetic information tests, and then pulling together what people are actually doing, both the health knowledge we know about them. So this could be things on the phone, Fitbits, things like that. But much more interesting is we also know that online behaviors can tell us a lot about people's, what's going on in their lives, but about them personally. So in other words, it's not suck all of this into some global thing and put it and then create the knowledge graph that everybody uses for a lot of reasons. Your personal health information wants to stay personal. Your personal online behaviors informing your health, you may not want to share all of that with the people over on the other side who are doing the mining. But if you can sort of put these things together in interesting ways through this kind of interoperability, then my phone knows me, the large knowledge graphs know that they get some kind of interoperability and some kind of communication. People are now working on things like distributed learning and things like that. So all of these things could be powered by getting these things to talk together. So how do we get there? So the starting place is starting from what we already know how to do and not reinventing some of the wheels. So some of the best parts of RDFS, OWL, and actually there are some other things. I know you've heard a lot about property graphs versus RDF model, and I'm actually going to talk a little bit about something that's missed in that conversation. And when I've looked at some of the slides, I think the property graph stuff have some advantages that we need to get into this other model, but this model has some advantages we need to get in there. I'll talk about that in a minute. But what some of the best parts of the RDF stuff does is a URI-based name scheme. And I'm going to go into that a little more in a minute, because I think that's crucial and has gotten lost, why that's so important. Then you can start reusing a lot of these heavily used vocabularies. And then one of the things that OWL has that really is important, and I'll may or may not get back into this again. I can't remember if I put the slide, and I was trying to turn like 4 1-hour talks into 1 half-hour talk. So obviously some stuff got missed. But equality statements turn out to be really crucial. So this is a slide I've been using since 2003 or 2004, but it sort of gets lost a lot, right? So if you think about the web, right? The web is seriously about hyperlinks. Now they're often hidden below web applications, hidden below JavaScripts and things like that. But it's still basically, the web graph is built by pages that by things that point at other things. So traditionally on the web, the very early web, you had a web page pointed at a web resource. It could be another web page. It could be a document. It could be a PDF document. It could be a picture. It could be pretty much anything you wanted. And that's really the basis, the heart of the web. And so what you were looking at is creating these kind of links. But RDF said, what you'd like to do is label those links. And what you'd like is the set of labels to be an infinitely large, well understood labeling system. Well, we have one of those on the web. It's called the URI, or URL when you're looking at documents, web pages. So rather than one URI pointing at another URI, now we have a URI points at another URI, and we label it with something. And that something is a URI. Well, that gets you something immediately, which is that those URIs are dereferenceable. So you can actually look at what's on, you can follow one of those URIs and actually your system can actually go look there. So the thinking in the semantic web was, if we had a common syntax, not a common semantics, and a simple semantics that would tie that syntax together, then you could do this kind of thing. So again, some of these are old slides and it would be a little more sophisticated now. But so here's an example that there's this document says we have this thing called a handler who is related to the thing that this particular website calls a job called the professor. And there's this other site somewhere called jobs that has places of work. And one of those places of work is this place of work. This was, my university. So I've defined this little thing about a person. So now when I, on a document, put something about this particular URI, then it's pointing at all those different things and it pulls them together. So it's like the knowledge graph, except some of the links can go somewhere else and they're well defined. And if you want to, you get two things immediately. If the same URL is used, same URI is used, then we know we're talking about the same thing. If different ones are used, we don't necessarily know if we're talking about different things. That's an issue we have to deal with in a minute. But if the same one is used, so mind : title jobs professor puts together something from jobs, something from our titling. Mine was my lab back at Maryland and my first lab here at RPI years ago. So these were things that you could use for the interoperability. And then you could start using some of these common things, but you also needed a way to tie them together. So OWL same as was invented as part of OWL. And there's some other things in OWL that do the same thing. So now I'm able to say, this guy in DBpedia, who DBpedia knows as a computer scientist, is this guy is the same as this person that Mind called Handler. And again, those could be different names, and I'll show you that in a second. And Handler has this title, professor, and blah, blah, blah. So now you can put it all together. So now you've got what looks just like the knowledge graphs you've been looking at, but notice we're linking together several different pages here. And of course, now those pages can be knowledge graphs that could be put together. And then using the same as and using the some other things, inverse functional data type, which is the worst named thing in the world, but very important. You can start building things like this. So these are just a few examples. So this was oh God, I don't remember how long ago, probably 2012, 2014. If you pulled my name and put it into something that looked up all of these same ases, so it would start, I would say, find me all the things that are the same as this Wikipedia thing by chasing through that open data cloud. You could find hundreds of different things in different places. So you can see my DBLP papers, papers on Sightseer, things from Wikipedia, things from my university. And, we had a lot of different examples of this. So a lot of people were playing with that. So the first thing that we need for this knowledge graph interoperability is those things we had back there. But there's also some other things we need if we're really going to go after this data use case, which is what's becoming the compelling use case, right? So we want the knowledge to be talking to the data out there. And I'm still talking simple knowledge, and I'll let Doug talk about why we need to extend some of that, or at least I assume that's what he'll talk about. So one of the things that was a real mistake in sort of some of the semantic web stuff is that we left out procedural attachment. And there was actually a reason for that. I have a talk called Wither Owl, which I'll mention in a second. And it talks about why we left some of these things out historically when we were doing this work. But roughly speaking, the real problem we had was that there was a patent on this stuff, and the patent hadn't expired yet, and we couldn't use something that somebody had patented in a standard without making everybody pay for it. But that patent has expired, and virtually everybody I've talked to who uses, for example, the medical ontologies that I believe you've seen, some of which, again, I'm blurring the term ontology, knowledge graph, RDF things, et cetera, because we're going fast. But whichever of those schema type things you're using, you're really talking about using something that gets you somewhere. But then if you have a database at the back, you really want to be able to use some kind of data query. So you really want to be able to say, when you get here, fetch this data, do this kind of querying, run this kind of process. And that's something we knew how to do for a very long time. And we even knew how to, if you were a logic purist who insisted that you needed description logics and all those things on the semantic web, which was another mistake we made, but don't get me going on that. You still need, we still knew how to do it. I mean, Prolog's been doing it for years. DL had ways to do it. DL went back when it meant description logic, not deep learning. So we needed that stuff. We needed some other things. And I have a talk on what we left out for data interoperability, part holes, temporal models, uncertainties. I would note that those are the things that actually are more easily done in property graphs nowadays. The problem with the property graphs is, again, they don't provide this dereferenceability, i.e. they're not URI based or embedded in the web in an easy way. And they don't typically provide that pointer back to something that has a base thing. So again, they're kind of enterprise-wide, application-wide, things like that. Very powerful, but not very interoperable unless you get these things worked out. So I have a talk on, it's a talk I gave in about 2016, and it was quite popular. It's on SlideShare. Doug, I thought you'd appreciate the fact that it's called Wither, W-I-T-H-E-R, not Wither, W-H-I-T-H-E-R.
I do appreciate it.
Yeah, so those of you who are out there and not so familiar, wither means to go away. Wither means where it's going. And I was trying to give a talk that talked about both those things. But anyway, also missing from this was privacy and security controls, which people have been working on now. And the other thing is a motivation for why to do it. And now there's a lot of systems I've been playing with. A company that I'm a consultant for on the advisory board of has played with this. And since I'm not pushing my companies, I won't talk about it much. But really, how do we pull stuff out of things that live primarily in the data world, use this semantic and knowledge graph infrastructure to put them together, and then hand them off to heavily used business and business intelligence tools, which monetizes opening and sharing these resources. So that's part of what we're trying to do. And that's another piece of learning. The other thing is, Vinay mentioned this, a little semantics goes a long way. Just to tell you how long I've been saying that, this is the T-shirt that my group had from the SHOE project, which started in 1996. I realize many of the Stanford students weren't born yet. And I don't think this URI does anything anymore, but the little semantics goes a long way does. Schema.org, which I believe has been presented in this class, was sort of what was started from Yahoo, then Google took it over in a consortial sort of way. And what happened was you ended up with a number of different, with basically defining some very, very simple ontology that nobody in the logical world would like as an ontology. What was based on was the things that are most used in search and such things on the web. So really, when Google took this over, and it really is a large part of what powered Google's knowledge graph acquisition, because they could learn a lot of it, but they still needed a lot of labeled data. And now you had all these different web developers around the world actually defining that data. So schema.org is literally on billions and billions of web pages now. If you look at the largest websites by, there's a bunch of different ones. I just like this one. It's used in all over the world. It's done, and it's terrible from any kind of meaningful semantics. So, for example, schema.org has 6 religions, which are 5 major religions and one called other. Now, nobody would say that's a great model of religion, but turns out if what you're trying to do is make money in the web by mostly trying to hit the top things, those are a pretty good set. Same thing with, person has, I think, 15, 20 properties. Again, not great for defining a person, but pretty good for saying, is this the same person as that other person? So it was used a lot in inferencing and things like that. So to conclude, what I'm arguing today is that we really need to start looking at interoperability again. Right now, most knowledge graph interoperability is provided by business relationships between the big players. But opening them lets us start, sort of finding new ways to play with them, more ways to create graphs and things like that, much larger knowledge graphs. And again, to tie it to these much more, when you can tie the big things to the smaller things, that's a win. So stress interoperability, learn from the past, avoiding overstandardization, reusing existing standards, and starting from successful business models. And I wouldn't be a real professor if I didn't hype my own book. So we're now in the 3rd edition of Semantic Web for the Working Ontologist, and an awful lot of what I've been talking about is available there. And I'll stop there.
Excellent.
I think I stopped.
Doug, it's over to you.
I'm just seeing a big black dark screen. There we go.
I think, Jim, you'll have to stop sharing so that Doug can share.
Yeah, I agree. There it is. Okay. My screen was just pure black for a while while it was coming out. There you go. All yours, Doug.
Doug, you're muted.
Okay, can you hear me now?
Yes, we can.
All right, great. And this is displaying?
Yes, perfect.
Great. So I want to talk to you about, in some sense, the complement almost of what Jim just talked to you about. But as you probably saw from my abstract, what I really am talking about is what can we do beyond what we call knowledge graphs today, and why should we, and how should we, and so on. This is really a talk about mistakes that were made and lessons that were learned, In some cases, in most cases, during the building of the Psych AI project, of which I was very happy to see 9 of you in the audience were part of. That's very exciting. During this time period, and what kind of an academic would I be if I didn't also at least touch on mistakes made before 1984 and also the mistakes I plan on making in the coming couple years, and so on. So I'll get to knowledge graphs around slide 32, which may horrify you, but I talk really fast and I'll be there in a couple minutes. So the first mistake that in some sense we made back in the early 1980s was focusing on content, focusing on the black space of what's written in text on paper, as it were. So we, around the time that the Final Encyclopedia came out, we talked about with Alan Kay and others representing the content of an encyclopedia, the things that the articles actually said. And we started to do that. We found a way to get funding for that. We started in the early 1980s doing that. But after about a year, we realized that a huge part of the iceberg under the water was common sense, the complement, if you will, of what the articles actually say, the things that the authors assume the readers already know about how the world works, that enables them to disambiguate ambiguities in language and to actually understand and reason with what's said and infer what's not said, for example, between the end of one sentence and the beginning of the next one. And so a lot of our work then shifted for fun to looking at things like the National Enquirer and the Weekly World News, saying, what is it we know about the world that causes us to be skeptical of what these articles and headlines are saying, and so on. So we also worked very hard to try to get sort of the upper ontology of distinctions as correct as we could. And in hindsight, I would say that that was a mistake, not a complete mistake, but we wasted a lot of time on it. And not just us. If you look at all of the ontologies out there, an awful lot of them have spent most or even all of their effort agonizing over this sort of notion of upper ontology. Probably we could go back and blame Aristotle for incorrectly telling us that we should be worried about symmetry and the number of categories and things like that, when in fact, all that really matters is that the totality of your ontology is adequate. This was driven home at a meeting we had where Ed Feigenbaum, who's here, was present at the Japanese fifth generation conference in Tokyo. EDR, Electronic Dictionary Research people presented, and they presented their version of sort of an upper ontology and psych and so on. And I was astounded because their upper level distinction was between things that had souls and things that didn't have souls. And big trees fell on one category side and little trees fell on the other. And despite a large number of culturally different ways of carving up the world, we still had no problems interacting with and understanding each other and so on. So all that really is impacted by the upper ontology, and not just the upper ontology, all of the distinctions that you make, and you could think of this as distinctions that you make in your knowledge graph, is really just a kind of efficiency issue. So even if you make horrible choices like grew and bleen, grew are things that are green by day and blue at night, and bleen is the opposite, you can still say things like grass is green, you just have to say them a little bit less efficiently. And so really it all comes down to how good your distinctions are they adequate? And if they're adequate enough, that's all that matters. And have you made enough distinctions so that you don't have all sorts of lost opportunities for traction because you're too ambiguous? So if you use the word smurf for most of your nouns and verbs, you have to be a lot more long-winded to get your point across. Or when we were building the psych ontology, to represent X being physically in Y, we eventually had to distinguish something like 75 different meanings of X being physically in Y, or else you get the answers to questions wrong, because the way that this dollar is in my pocket is different from the way that the sugar is in my coffee, and so on. And the same is true with other words like have and with, and so on. And in a way, it's our common sense which enables us to cope with this level of ambiguity. If you're a machine and you don't already have common sense, then the less ambiguity you have, the better. And the better your ontology, the more efficient things are, the terser the axioms can be, the terser your assertions in your knowledge graph, if you will, can be. And that's better for humans who have to write them. It's better for automatic programs that have to try to learn them. It's better for an inference engine that has to reason with them, and so on. Another thing we learned was that you don't really want to have a larger ontology than you need, because then you start having multiple ways of saying the same thing. Like in English, there are an awful lot of ways of saying the same thing, and that's why natural language processing, natural language understanding is so difficult for computers. And the more ways you have of saying the same thing, if you don't want to lose traction, if you want the deductive closure to stay the same, you have to actually interrelate them. So for instance, if I want to say that the sun is yellow, I might say it's a yellow object, or it has yellowness, or its color is the yellow color, or it is yellow colored. And if I really have the vocabulary for all those things, then I have to start writing all the n squared axioms that interrelate all that vocabulary to each other. So that was another important lesson. Maybe a good example of something that's just at the point of being worth or not worth defining might be black and white cats. There's a lot to say about black cats involving witches and superstitions, but really, what are you going to say about white cats other than they're white and they're cats? So it probably doesn't deserve its own term in your knowledge graph. And then finally, we're getting to a relevant thing, I think, for all of you in the audience, which is that we started with a representation that was not expressive enough, and kicking and screaming, we had to slowly make it more and more and more expressive. So the representation that we started with is more or less what you would call knowledge graphs today. Back in those days, we had lots of names for similar things like actors and beings and frames and slots and associative triples and object attribute value pairs and property lists and all sorts of things. But they all boil down to more or less the same expressive power as you're familiar with knowledge graphs. And so why were we forced to more and more expressive representations? Well, the simplest example is wanting to represent things that were not just binary relations, that took more than just two arguments. So if I want to say that LA is between San Jose and San Diego along US 101, there are several of these concepts that deserve to exist. And if I have a relation that takes four arguments, like between along, I can say it this way. If I'm forced to use just triples, then I have like a very large number of triples, which in some sense don't really mean anything in and of themselves individually. And it's only the bundle of triples that mean something, in which case you might as well have the higher arity relation. So why care about this? It's really the reason why we don't all program in machine language anymore. Moving to assembly language and then higher and higher level languages and so on makes there be a much closer impedance match between what you want to say and how you're going to say it. And so that moves us along, as Ed would call it, the spectrum from how to what. And that turns out to be enormously powerful The farther along you can move that. Just as a trivial example, natural language generation is much easier to do. So I can have one natural language generation template for that quaternary relation, and basically translate that into a natural sounding sentence. Whereas if I were just translating those triples, that would be a lot uglier and messier and harder to understand. Another example of why we were pulled farther than just knowledge graphs as a representation was that we wanted to represent lots and lots of logical connectives, not just the ones that knowledge graphs permit. So to move away from things like negation as failure, to be able to talk about the quantifiers like for all and there exists, and the nesting of quantifiers, because while these sentences look very, very similar in English, of course they mean drastically different things. And if you represent them in logic, in say first order logic, of course they look very different. In one case, we're talking about the same king. In the other case, we're not talking about the same mother. And other sorts of quantifiers are things like there exist at least or exist exactly, and things like that. We wanted to differentiate relations that are transitive, like subset of or generalizations, from those which are not transitive. So the set of numbers from 1 to 10 has 10 elements, natural numbers from 1 to 10. It's a finite set. There are an infinite number of finite sets, but of course, the integers between 1 and 10 is not one of those infinite sets. It only has 10 elements and so on. We want to be able to use variables and ask questions like, how are Jill and Joe Biden related? We wanted to have variables in the predicate position, which is a second order thing to do. We wanted to be able to refer to various meta level things like, who told me this and why should I believe it and when was it true and how has it been useful in inference in the past, and what have I tried so far to answer this question, and how successful have I been, and maybe I should change tactics and so on. We want to be able to represent counterfactuals like what if this were true, or sort of qualitative likelihoods and various kinds of modals and nested modals involving belief and desire and fear and expectation. And this is not just some arbitrary philosopher saying it would be nice if we could, ... If you turn to almost any news report, conversation transcript, you'll see all of these kinds of things like nested modals appear all over the place. I can say to you, when Juliet drank the potion that put her into suspended animation, did she believe that Romeo would believe that she was still alive? And the answer is yes. And you don't have any problem answering the question. You certainly don't have any problem understanding the question, and so on. And if I asked you to, you could explain your answer. If we look at the New York Times from a couple days ago, we see similar sorts of things. It's hard to imagine representing the content of this as a set of triples without throwing away, 95, 99% of the content that's here, without throwing away 99.999 something % of the things which you could infer, or the writer expected the reader to be able to infer, having read and understood this article, and so on. I could give you a dozen more examples of things like this, but you see the sort of impedance mismatch problem, like for example with Joe is mad at Sam because he stole his lunch. So in English, we make one tiny change from the because to so. Joe is mad at Sam, so he stole his lunch. Now the he and his in the first sentence are obviously Joe was mad at Sam because Sam stole his lunch. But in the second one, Joe is mad at Sam, so Joe stole Sam's lunch. And so we have no trouble understanding these, or understanding that if I say this thing about appendectomies, since people generally don't have more than one appendectomy, I really meant or rather than and here, and so on. So by about 1989, we sort of had moved to the point where we realized we would need higher order logic and modal logics to represent all this. So how could we possibly get this to be efficient? That's the reason that really everyone stays in the shallow end of the representation pool. So the problem is the fact up there that representation was singular rather than plural. As I often say, we're really talking about right versus left brain reasoning, but all of you knowing about knowledge graphs are sort of here on the left brain side, but there's still this choice of, even after you make this commitment to left brain reasoning, how expressive is your logic going to be? Are you going to be satisfied with knowledge graphs, or do you want to move to full first order logic or to higher order logics and so on? So why not? Why stay in the shallow end? Well, obviously it's because there's this trade-off between how efficient it is to reason with things represented a certain way and how expressive that representation language is. And at one extreme, you have like natural languages and higher order logic. At the other extreme, you have sort of, machine learning and machine language and so on. So really, taking a lesson from war games, the only way to win this game is not to play and essentially say, we're not going to make a trade-off. We're going to separate the epistemological problem of what should the system know from the heuristic problem of how can it reason efficiently with what it knows. So that means we're going to have multiple representation languages and a translator between them, sort of like the Eloi and the Morlocks, with the Eloi being, let's say, philosophers working at a nice, clean epistemological level, and the Morlocks being inference programmers, down grubbing under the surface of the earth to make things efficient. And so we basically represent things in at least two ways in psych, at an EL and at an HL. And actually by now, we have over 1,000 different ways of representing things, over 1,000 different representations and HL modules and so on. And I won't really go through the reason why I'm not paying much attention to the numbers here, but essentially you can change things from 10 to the 22nd things you have to say down to like 10 to the 4th things you have to say by being clever. And so a lot of our people's time, and again, several of you in the audience have been people working with us on this, is spent being clever, policing things, looking for ways to generalize so that things happen in a small number of axioms rather than some astronomical number of axioms. And having representations like the paragraph above are fine, but if you realize that you can re-represent that as 5 linear equations and 5 unknowns, then you can solve that in about 1 minute versus 5 or 10 minutes or giving up. But anyway, the chasm persists all this time. And there are lots and lots of other mistakes we made and lessons we learned. I don't have time to go through them in detail, but I'll sort of race through a few of them just so you can get a sense of what they are. There are about 150 lessons altogether. I'll race through about half a dozen. 150 breakthroughs sounds like a lot maybe, but if you divide by 37 years that we've been working on this project, it's a little bit less impressive. But anyway, one of them is something that Mike certainly knows very well, that he and I worked on together back at Stanford decades ago, which is the fact that you can often gain enormous efficiency by a judicious use of meta-knowledge and even meta-meta-knowledge. So you have sort of rules and meta-rules and meta-meta-rules and so on. And maybe 90% of your time you're actually solving a problem, but a little bit of the time you're doing meta-level reasoning, and that makes a huge efficiency gain. Rule macro predicates are just a way of saying, oh yeah, here are these complicated schemas, but they recur so often that we're going to define a whole new predicate, in this case, a simple ternary predicate that captures the meaning of that schema. So now I've turned and if-then rule into a GAF, a ground atomic formula. And reasoning with GAFs is enormously efficient compared to reasoning with logical formulas in general. So another example was we had this proliferation of inference parameters, like how many inference steps should we allow? How many backchain steps should we allow? How many new concepts can be created? And so we eventually had something like 150 different inference parameters that were like little dials you could set whenever you were doing asking psych a question. And one of the empirical lessons we learned was that, in fact, if you just pick 6 combinations of those parameters, those 6 combinations suffice to give pretty much the same answers on the last million questions that psych was asked. So you don't really need all these, you only need these little 6 settings, and you have one dial with 6 settings that replaces all of that aggravation. I'll go through some examples of what I mean by the efficiency. This was another example, but just to show you a quick demonstration so you can see what I mean by answering these questions quickly. So here we're asking psych, would humans dislike touching incandescent light bulbs while they're on? And psych is saying, yes, and we can ask why, and it will tell us sort of why, like humans don't like feeling pain, and it's like really, hot. And so underneath all this is the underlying psych-L, and it's generating these expressions in real time. But to take something dramatically more complicated to ask and answer, we could say things like in Romeo and Juliet, when Romeo tries to buy the lethal poison from the apothecary, what are the apothecary's pro and con reasons for selling it to him? And like, well, it's a con reason, which is basically at the time of the play in Mantua, Italy, it was punishable by death to play the role of the seller in a buying, selling of lethal poison. And then on the other side, essentially, was, well, the apothecary's family was starving, and he really didn't want his family, his loved ones, to starve. Or to give an even more dramatic example of a counterfactual hypothetical question, how would Lord Montague have felt about their wedding if he had known about it? Well, he would have felt great abhorrence, but I could actually do things like say, let's enable premise rejection and so on. And now I could basically look at the justification for this and say, oh yeah, it all comes down to the fact that at the time of the play, these 2 houses were enemies. What if they weren't enemies of each other? Now I could go back and ask that question again, where we're assuming now that it's just a medieval city in Italy where the children of 2 ruling noble families are getting married. And so it's psych is reasoning that, oh, well, he probably would have then felt approval toward them and so on. So part of what I'm showing you here is to show you that the reasoning is fast. It can be effectively in real time. The expressiveness is there. The ability to represent it is there. The ability to do the reasoning is there, and so on. I'll give you a secret lesson learned, which was people kept complaining because every now and then psych would fall through all these 1,100 special purpose reasoners and call on the guy in the back who always had his hand up that you never wanted to call on unless you had to because he was so slow, which was the general theorem prover. And it turned out that any question that psych had that it had to call on the general theorem prover, it ran out of time for. So we just very quietly turned off the general theorem proving module about a decade ago, and no one's ever noticed. So that was sort of an exciting thing. And yes, I know theoretically that's like a terrible thing to do. And if you want, you can turn it on, but it's just going to be something you regret. We also made some mistakes about what we thought people would want to share, that we thought that they would understand that just sharing the ontology, the taxonomy, the knowledge graph would miss the critical information. It's nice to know that, terms like person and sleep and night and so on. But if you don't also have the knowledge that people sleep at night, they sleep for several hours, they sleep with their eyes closed, they sleep lying down, they can be woken up, they don't like being woken up. If you don't actually have the things that are the complement of the ontology or the knowledge graph, then you're throwing 90% of the baby out with the bathwater. So despite that, people grabbed OpenPsych and they were happy with it, when in fact the whole point of OpenPsych was to show everyone in the community why that wasn't actually enough. To answer Jim's what he thought was rhetorical question, what you really need for this sharing is to share enough of the content as well as enough of the ontology and enough of the context, because all these different ontologies really were built in different contexts and different time periods for different purposes and so on. So you're not going to have one nice consistent one that could unite them. So you need to have the context be explicit so that you can reason about the interstices, just like you reason about the interstices of tectonic plates that sort of push against each other, even though each plate is rigid and flat. Anyway, one of the things that we introduced into Psych early on was explicit context as first-class objects, which is easy if you're using higher order logic. Otherwise, you have to do some kind of partition networks if you're using something like knowledge graphs. And we moved from this notion of globally consistent knowledge to knowledge which is only locally consistent. Like, you know that the surface of the Earth is more or less spherical, but you live your life every day as though it were flat. And that's okay because it is locally flat. It's a two-manifold. And occasionally you get into trouble, but if you're talking to someone in Australia, you rarely think about the fact that they're upside down orientated to you and so on. And so in much the same way, the knowledge in Psych is only true by default and is highly contextualized, and you can never really fully contextualize anything. I could talk about the dimensions of context space, but I think in the interest of time, I'll just make a few remarks about the fact that almost nothing is absolutely true. Almost everything is only true in context. And that also means that when you're asked a question, your system should in fact find the pro and con arguments for and against each answer, not operate in a mode where it's finding one answer as though there is only one answer, or having the hubris of thinking that the best answer is objectively definable and so on. Now, the next mistake, and you may get a kick out of this, was taking everything I just said way too seriously, because very often you know that you're solving a problem where, in fact, you can ignore everything except this small set of knowledge, or you know that while you want the system to be able to accommodate new knowledge, nothing is going to be learned from the outside world while I solve this problem. Or you know that you're assigning professors and students and classrooms for classes next semester, and so SAT constraints are all you need, and you know maybe in some problem that things are going to be consistent and so on. So I could go through lots and lots of additional pitfalls that our ontological engineers have gone through, but I think that at this point you sort of get the idea, and we could talk about taking variable names and term names too seriously, about overgeneralizing things that in fact are really default false, about over-specializing things like this, where in fact something much more general like causes precede effects is really all you need to represent, and so on. And I guess the final mistake or the final lesson learned was that we really need to map And we have been over the last 10 or 20 years mapping Psych to different ontologies, to different databases, to web services and machine learning systems, and so on. And as I said, there are about 150 of these, and I've only covered about half a dozen in any detail. And it looks like we don't have enough time, unfortunately, for me to tell you about the mistakes I intend to make in the next couple of years, but maybe that'll come up during the question and answer session. So let me stop at this point and turn things back to our moderators.
All right. Thanks, Doug and Jim, for those outstanding and thought-provoking presentations. We have about 20 minutes now for questions and discussions. There are some questions that have been posted in the chat. So let's just pick something from the questions from the audience. So there is a question: what will cause big companies to open up their knowledge graphs for interoperability?
So, I think that's the big question. And, I have a few different historical answers and one, business answer that we're, kind of betting. I know at least one company that's being bet on. So the historical answer is interoperable small things are the only thing that can challenge non-interoperable big things. The most famous example I can think of is nowadays when you go to Google, when you go to Amazon or any of those things, you not only get what they'll sell you, but also what lots of other people will sell you. So in the early days, a bunch of the bookstores, like if you went to Barnes and Nobles, you only saw what Barnes and Nobles had. And if you went to Amazon, you only saw what Amazon had. And then a bunch of smaller bookstores started saying, hey, if we cooperate, we'll get some of that business, and 20% of that business would be great for us. And they started taking away the tail of a lot of that stuff, and that forced those other guys to sort of open up their stuff to so now the agents that wander through everybody's stuff and all those kind of interoperability things became standard. And you see a lot of places where silos, the only thing, they either win, Facebook, or they lose because they get challenged by lots of small things together. Schema.org was one where none of the search engines could get anybody to do this alone, but once all the search engines started endorsing it, they got further along. So I think that same model saying, we have a lot of small companies that have built some very specialized knowledge graphs, and together we can start to challenge some of the bigger guys. The bigger guys are then forced either to open up or to buy us. And the specific business case I mentioned in passing was a lot of these business intelligence systems need you to pull stuff from different databases. And mostly that's being done now within your enterprise. But now when you start to get some of these open enterprises, so we are a consortium doing things and we don't have a single agreed upon standard in our data, and we don't have the money to recode everything. But what we can do with some kind of interoperability is pull our stuff together and then throw it into the common business tools. So we only need to do n to one and one to the tool as opposed to n squared kind of thing. So I think it will be those same kind of arguments.
Okay. So given that, Jim, you feel that semantic interoperability for knowledge graphs should be the next thing, that raises the question in my mind that semantics is what Psych has been about throughout its history. And the question for Doug would be that if, let's say, we wanted to solve this problem of interoperability of knowledge graphs over the web, what 1% of Psych we could bring to this problem?
Yeah, so I guess I would say that part of the problem, this actually gets to Omar's question. Part of the problem is assuming that there is some 1% like that. In a way, that's like saying, well, we want to hire a new petroleum engineer. What 1% of his brain should we allow him to retain or allow her to retain? I think that the key to having the kind of interlingua that Jim was talking about is basically having enough of the territory covered that in fact you can, just like you would with one human being looking at a database schema, you can explain to, in this case, psych, what the meaning of this schema element is, what the meaning of that relation is, what the meaning of that concept boundary is in this particular ontology or that one, and so on. And it's only through doing that, I think, that we're really going to see that kind of integration. This was something that was learned really early on in the Stanford Heuristic Programming Project, when people took sets of if-then rules, which individually these sets work perfectly fine for different applications. But when you try to just union them together, horrible things happened, either errors of omission, because these people use different terms, and so these rules passed like ships in the night, or even worse, they used the same terms to mean something different, and they would collide, or one of them would make all sorts of assumptions that the other ones didn't.
Okay, so maybe you're saying that I shouldn't be asking what 1% to take. The real answer is we need to take 100%. And let's say we agree to that. Then the next question that I think several people are asking is, how can we go beyond just 100 people working on psych versus other people sort of participating in that effort? And how can we take a more expressive kind of approach and promote it to audiences or companies or potential buyers? Because that's a real challenge. It's not very easy for us to convince people that, they need to go more expressive, because they can't even get less expressive things to work, right?
Right. So I think that the answer has to be moving toward some kind of knowledge utility, in analogy to electric utilities, telecommunication utilities, and so on, where you have such enormous economies of scale that the actual cost to individuals is negligible. So even though these industries are making lots of money, it's been a long time since anyone looked at you askance for plugging your phone into the wall to recharge because you were using 1/1000th of 1 cent of electricity, and so on. And so I can imagine various ways, just like we have with electricity, where you could hook up solar collectors. I could imagine for people who can't even afford the tiny amounts that this would take, to have some sort of knowledge economy where you have micro transactions, micro credits being asserted. So you could contribute some knowledge to psych. So just like you're pedaling a bicycle to pay back your electricity that you're using for the next 4 hours, you might have to contribute 4 pieces of knowledge to the system in order to earn enough credits to ask your next 12 questions or something like that. And because because psych knows exactly who contributed what, you can basically decide, oh yes, this person gets 3 billionths of a cent for this other person having asked this question, and so on. And gradually over time, you get to a state where you've got this economy of scale. And so I think anything we could do to jumpstart a national knowledge economy, like I just described, is the way that we can get to this state where, just like the ARPANET dream was to have computation effectively free, and today computation really is effectively free. What I'm talking about is how we could get to a scale where, for all intents and purposes, reasoning would be free. And I can't imagine any more worthwhile goal for us to have.
Okay.
So Vinay, let me weigh in on that too from a different angle. So, interestingly enough, Doug mentioned that Ed Feigenbaum is or was on. Doug and I have both published co-authored papers with Ed, and they both had the same title, Knowledge is Power. Mine had a different subtitle. And we were using the analogy in the second article of batteries versus what was being used in the first article was sort of dynamos, what Doug just described. And there are times, when I'm carrying you can't see my cell phone because I have a background, but when I'm carrying my cell phone, I don't necessarily want it hooked into a dynamo that I carry on my, I don't want to have to plug it in, right? So again, I think that when I talk about little semantics, I'm almost talking about a bottom-up way of getting somewhere. And when Doug talks about big semantics, he's talking about top-down. But I think that anybody who thinks that those are not things we could do together or that could both happen or that can both live have missed what the past 25, 30 years of the evolution of the web and similar kinds of large-scale systems show us, where it's the linking of lots of little pieces is one kind of power, and the building the sort of monoliths in the middle is another kind of power, and the biggest power comes when you put them together.
I actually disagree with you, I think, and so I'm going to put on my keep your distance, Jim, hat.
Yeah, well, Doug and I were once at something where, as we were going in, Doug said, it's important that these guys believe we're both on the same sheet of paper, even if we're really on different sides. I mean, certainly from the number of angels that dance on the head of the pin, Doug and I are closer than a lot of other people.
All right, I'll switch to this one, this vaccinated one.
All right. So, Mike, did you have a comment to add here?
Well, I had a question to ask, but I'm sorry.
Yes, please go ahead. Yeah. Please go ahead.
The virus here. So one of the things that's happened in psych is you started off with, to some extent, an HL focus, and then this EL, and then HL came in. And I'm kind of curious if you had never brought in HL, if you had sort of taken a team and sent them off and said, do the EL approach, the epistemological approach, and just ignore the H stuff. Would psych look the same right now, and could it be used? What if different people were doing the H from the E? I'm really kind of curious about the interplay between those two.
Right.
Just comments on that.
That's an interesting question. I think that the answer is certainly now we could have different teams working on them separately, and in a way you could think of each of them being the customer of the other team.
Exactly. Yes.
And in a way, that's what actually happens today. So we have a new application. One of the questions was about application. So we do things like helping to predict what's going to happen with patients as they matriculate through hospitals, or what's going to happen with this oil well that's being drilled, or what's going to happen as we try to fabricate, given all the uncertainties in supply chain. So we have some new application. And as we build this new application, people at the EL put in the new knowledge, and suddenly they find that things that the experts are doing that only take them, a second, now takes like 3 minutes to come up with the answer. And so we basically say to the experts, hey, how is it that you're able to do this so fast? And they'll say, oh yeah, we represent things this way. We apply this known algorithm or formula over here. And that's how we're able to balance this equation so fast, or whatever it happens to be. And so we take the null hypothesis that you don't need any more HL modules. And then in application after application, it turns out, yes, you do, which is why we have over 1,000 now.
Yeah. So the question is, could you ever be happy and sort of say that we're epistemologically adequate? And we don't, and yes, H, we got to add some H stuff for H purposes, but epistemologically, we're adequate.
Oh, I'm sorry. I misunderstood what you're asking, Mike. So yes, I would say it's been really on the order of a decade or 15 years since we've had to modify the EL in the sense that you mean. Of course, we add new terms for efficiency reasons and so on. But in terms of the semantics of the language and what could be expressed, that it's been a long time since we had to make any changes there. So all of the tinkering we're doing at the EL is really more for naturalness and terseness reasons rather than any kind of expressivity reasons.
Yeah, that's what I was looking. The other part's interesting too, but that was actually what I was after. I've always been concerned with the fact that some people who see those magnificent demos, those fantastic examples you give, keep thinking there's a lot of Doug there, and that's you were answering the question produced by that was relied on your EL the epistemological version, and you were asking the questions. But what if somebody comes along and asks a new question? Can it answer it? Not can it answer it fast, but can it answer it at all? So it's nice to know that the EL is actually pretty solid at this point. That's really what I found interesting.
That is important. And I will say that for example, the Romeo and Juliet questions did answer expeditiously, in the sense that we didn't have to change the questions much, but not expeditiously in the sense that we had to tinker at the HL in order to make a lot of that deeply nested reasoning about what does X believe that Y believes that X believes about Y happen really, really quickly.
Right.
Okay. Well, so I think that's a fascinating discussion. I'm sure Mike can go on this.
Yeah.
I was going to say the logicians can always go on it late.
That's right. So I think the thing that I'm wondering about is that in the real world, knowledge graphs are where they are, right? There are silos, and people are doing the things that we see, Amazon knowledge graph or Google knowledge graph and smaller knowledge graphs. Given that is the reality, where do you think we are to be in next, say, 3 years or 5 years, right?
So Vinay, I would use the following analogy. We used to joke, we still joke in some places that, ontologies are like toothbrushes. Everyone has one and no one wants to share them, except that now there's a lot of shared ontologies out there. Look at Wikidata, right? It's now being used to power all sorts of things, but then also look at the bio-ontologies, right? NIH is getting a lot of pressure. They want to stop funding some of that work, and biologists around the world are saying, no, you can't stop funding that. It's essential to our ability to function. So again, we're definitely seeing sectors and niches where you have large things in one place, small things in other. It's pretty much wherever anybody needs agreement. And then you also have enterprise ones, which are just agreement within something. The average enterprise web today, intraweb, is bigger than the web was in 1995 when, it first came out and everybody said, wow, look at the web. So, I actually think history shows us that the only thing that wins is large and small and things starting to move together. So I think as KG technology becomes easier and easier to deploy in small applications, then people will start finding the business models for this kind of linking. And whether, Psych is the middle, Wikidata is the middle, lots of other things are the middle, or, when my personal belief is why have a middle? That's kind of what seems to work in the real world. And it's one of the only things that works in the real world to really get growth.
I have a surprisingly concrete and different opinion, Jim, which is I think that if you look out 5 years, what you'll see is yet higher level language, one level higher than everything we've been talking about in terms of psych and knowledge graphs. And what do I mean by that? I mean that we've finally gotten to the point now where I think psych itself is able to actively help with the use and extension and mapping to third-party sources itself, which is very exciting. I'll give you one short example of that, which is a tool for doing abductive reasoning. And so people who don't even understand AI, who don't understand logic, who don't want to find out anything about psych or epistemology or even knowledge graphs can use it. And essentially what happens is you're building an application, you ask a question, it gets the question wrong. The expert says, here's the right answer. And then psych uses everything it knows about common sense, about the domain, about discourse, to say, oh, well, here are 10 things which are plausible. And if any one of these had been true, I would have gotten the answer you just told me I should have gotten. And then the expert who doesn't know anything else looks at those and says, oh yes, number 7 is the thing that's true. And so by doing a better and better job of these knowledge editing and knowledge building and knowledge debugging tools, and we have about 40 of these tools now, like I just described, I believe that the whole notion of what it means to use and build and interrelate these ontologies will actually change and become much more of a kind of hidden infrastructure rather than the kind of bare wires being twisted together by engineers, which is sort of what we're still at today.
All right. Yeah, I mean, that's fair enough. I mean, Doug's argument is, well, let's keep doing what we've been doing, right? And eventually it will hit the real world. Well, we are nearly at the end of our time. Perhaps we could conclude by requesting each of our panelists for their thoughts on what mistakes they would like to make for next few years. Jim, do you want to go first?
Yeah, Doug's never let me have the last word. Okay. I think the mistake I'd like to make is looking at the many different ways this stuff can play out and not yet standardizing on a business model. So I think we don't have in the knowledge graph world yet quite enough of a, let me call it a common base, a shared something such that we're quite ready to do that. So schema.org for knowledge graphs isn't there yet, because we don't quite know what the use cases that will really power that. So a lot of the questions on the Q&A have been, sort of, okay, so what do we do with this? And my answer is, we're still figuring that out, but, we can already see academically this stuff coming. But, we were playing with a lot of the interoperable, knowledge systems long before the web came along. It's just, it really figured out how to get it right. And then on the web, I could give you that same story over and over and over and over again, where sort of something starts to grow, gets interesting, becomes a de facto standard, different models make it, we're different business models. And so, again, I think years ago on the sort of semantic web space, I said, our problem isn't the chicken and egg anymore. It's the building the farm, the process farm. I think knowledge, and we have now, and schema.org is one example of it. And if I had time, I'd go into a lot of others. I think that we see that same thing, and I see that same thing in knowledge graphs. It just feels very familiar. Every time I go to a knowledge graph talk, I feel like I heard this before 20 years ago.
Okay.
There are differences, as I've talked about today. They're not the same, but yeah, that would be my thing. So I think what we really want to do is try lots of different things, make lots of mistakes,
okay,
and evolve the right things.
Excellent answer. Doug, what's your take?
So the mistake, although I hope it's not a mistake, but the potential big mistake is going to be assuming that the kind of infrastructure, the kind of knowledge utility scaling will happen, and that in fact, an enormous number of people in the world could be very quickly brought up to speed to using the more powerful, the power tools that I was describing, and could be brought up to speed in doing ontology and axiomatization work and so on. In fact, we've started something called the Knowledge Axiomatization Institute, which believes that we could actually find people with latent talent for doing this, including high school dropouts and so on, because there's no real correlation between the current education system in the US and in the world and ability to learn to do this and train those people, put them through a kind of core training to get to the point where they could be sort of ontological engineers and have an entire career doing that and so on. So there's several bets that we're making, and it's possible that one or more of those bets will turn out to be mistakes. But I still think it's in the best interest for the world, for humanity, to make those bets and hope that in fact they pay off.
Yeah, no, I think that sounds very exciting. This whole idea of Knowledge Axiomatization Institute, I had not heard that before, and I'm glad that you're willing to bet on this. And I just hope that it doesn't turn out to be a mistake.
We just got our approval from the IRS for it to be a 401c3 charity.
Great news, great news. Excellent. So we are already over time. With that, I would like to conclude today's session with a word of thanks and gratitude to both of our invited speakers. It's been really a blessing to be with both of you today and to hear your perspective and hear your thoughts. This is also the conclusion of our Spring 2021 seminar series. I'll also like to thank participants in our class as well as guests who have been showing up here every week with full devotion. We've learned a lot with all of you. So thank you all very much. And hopefully we will continue some form of this series again next year. Thank you all very much.
Thanks, Jim. Thanks, Doug. Good to see you both.
Same here.
Hope we get a chance to do this again sometime soon when we're going to have more time to chat.
Yeah.
If I don't know if people have their emails publicly available, but there were a whole bunch of questions in chat that we didn't get to. If you could copy the questions and send me information for contacting the people or some way of getting responses back to them, I'd be happy to answer this.
Sure. Yeah, I mean, maybe the easiest thing is to say that they could write to you at doug@psych.com.
Yes.
Right? It's DOUG@psych.com, cyc.com.
Yeah, and I'll make the same offer. Send them to me at hendler@cs.rpi.edu, or just put my last name into Googling and find it. But please tell me you were here, because I get a lot of random questions and don't have time to answer everything everybody sends me. But I feel people who gave me the time, did me the honor of spending their time listening to me, deserve my time in answering their questions.
Exactly. It's fantastic that you guys have set this up and are doing this. So
yeah.
I really applaud you're doing this. Thank you.
All right. Thank you.
Okay, folks. See you later.
Okay.
Bye-bye.